It'll be the 17th. There may be some slop in that. The problem is commencement. They don't like me to have classes on the day of commencement. So I usually end the semester before that. That's why it's the 17th. Okay, so we are going to start way back. And I call it the history of science because it really wasn't the history of the atomic model because they didn't know about the atomic model. Now we're talking thousands of years ago, back in the Greeks. And they had an interest in what we're walking on, what this stuff. What is the stuff made out of? They had no idea it was going to be so hard to figure that out. Okay, so now interesting thing about science. Science is a moving target. What I mean by that is when we get data, we try to rationalize the data. And then we test that rationale. And that's called experiments. And if the experiments are consistent with the new idea, then we kind of keep it around and keep testing it. However, if the testing is not consistent with the data, then maybe we need to rethink what the data represents. And that's the thing about science is it's a moving target regarding what data do we have today versus data yesterday. So a lot of people are very narrow-minded regarding science. They don't understand this concept that there is no absolute in science. It's based totally on the data acquired. So if we have an alien land out here tonight, tomorrow's data is going to be different. Has anyone had any extraterrestrial experience? I had one a long time ago. I was backpacking. I used to backpack a ton when I was younger. And we were up at the Sierras, just above Emerald Bay at Eagle Falls Campground. And we're lying in, I rarely brought a tent. We're lying there looking at the stars. I was with a companion, female companion, just FYI. And we're looking at the stars, kind of talking about the stars, And I said, oh, look, there's a shooting star. And all of a sudden, the light went like this and then stopped. Now, celestial things don't stop. They keep going or they gradually disappear. This was like that. And then it went away, never to be seen again. That's the only experience I've had that I can't explain it. And because satellites kind of act like a fast-moving star, planets are the same way. Stars twinkle; they don't move visibly anyway. So it could have been a super secret Air Force thing, or it could have been something else. But it was interesting, and that's the only experience I've had. So, okay. So back to this whole thing on science. I just want to make sure you understand that science constantly changes because the data changes. And that's what's one of the interesting things about AI is because AI's database, it draws information from, doesn't change until the next upload. When the next upload comes, then their conclusions based on the prompts or their outputs change. So remember that when you're using Chat GPT, is that's only truthful based on the data that was given it. So stuff that happens today and yesterday will not be included in that output of your Chat GPT. Now, I use Chat GPT all the time. I have a proposal that has met with mixed reviews regarding using Chat GPT in class. And one of them is to take the student learning objectives for the course and using Chat GPT to generate a textbook based on those learning objectives. And everyone says, no, you need a teacher involved. You do need a teacher involved, in my opinion, also, more as a guide rather than a source of information. And that's has met mixed reviews. The deans are the ones that like it the most. Fellow teachers don't like it as much. Very interesting. So, okay, anyway. A lot of things are kind of weird. What do you see in this picture? Do you see one person or two? Yeah, it depends where you're looking at it. Same with this guy. Who's hugging whom? It depends on your angle, on perspective. Which circle's bigger? They're actually the same size. Wild stuff, and we are subjectively looking at this. Now, subjectively versus objectively. Subjectively means we're depending on our 5 senses to judge these. Now, my 5 senses and your 5 senses probably are not the same. One, for example, hearing. During the test last week in my organic class, there was a blower that was going off and on. It was bugging everyone. And I said, what blower? I didn't hear it at all. So my perception of that sound was different than my classes, subjectively. Objectively, to get around that, we use an instrument to measure it. Totally leaves us out of the loop. Things like color. You're colorblind. You don't see the same as someone else. Taste. My taste is lousy because of COVID, which is going to differ greatly from your taste, unless you had COVID. Okay. A lot of interesting things here. We don't want to do a first quiz. Okay. So let's kind of start from here. We had a number of people. Now, this is again like this is like BCE 1,000 years. BCE 1,000 years ago, it was like over 3,000 years ago. Okay, there was a number of people at that time that in thinking about things, particularly matter. One of them was Aristotle. You've all heard of Aristotle. Aristotle believed there were 4 parts: earth, air, fire, water. And that is not the name of a band. What's the band? Earth, Wind, and Fire, right? Okay, Aristotle was very popular in those days. Very, very popular. So popular that his idea of everything being made of earth, air, fire, water lasted up until the 1700s CE. That's thousands of years later. There's a little known guy named Democritus, however, didn't believe that. Well, this is his concept. If we take an apple and a knife and we chop that apple in half, do we still have an apple? Yeah, half an apple, still got an apple. We chop it again, still got an apple, right? We keep chopping away, and all of a sudden, we don't have an apple anymore. So Democritus said that is the no cut part of that original apple. And no cut in Greek is called atomos. And that's where the word atom comes from. Democritus. Meanwhile, Aristotle's running around earth, air, fire, water. Now, we're talking about getting into European philosophers. Some people called them alchemists. Some people called them philosophers. No one called them chemists or physicists. And their reason for being, from a king's perspective, was to take cheaper things like lead and convert it into gold. Now that's called transmutation, and we do that all the time in atomic physics, nuclear chemistry, even just out in high atmosphere here, we do this. But in those days, they were trying to take lead, convert it to gold, and they were having a lot of problems doing that. The other thing is they found something called fool's gold. Now, most of you have probably heard of fool's gold. If not, it's an iron pyrite that looks just like gold, except it's not. It's shiny, kind of yellowish, but it's much lighter than gold. So its density is different than gold. In fact, that's how the merchants, when you brought your gold in to be converted, that's how they determine whether you had gold or iron pyrite, which is worth nothing. Okay, number of things were going on with the alchemists. They're trying to find the elixir of life. So when they weren't trying to convert lead to gold, they were trying to find the elixir of life. They believed in something called ether, which was supposed to breathe life into living things. All very hand-waving stuff. Now, there are a couple of problems with alchemy. In today's science, when you save the world, I have blah, 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 you've got to be able to prove it. Not only you have to prove it, another lab has to duplicate what you've said. If they cannot duplicate what you said, what you say can't be validated. Now, there's a lot of controversy in that, what I just said. There is a major Japanese lab, been about 20 years now, came up with a new element, but no one else could duplicate their work. So they disavowed knowledge of that new element because it could not be repeated. Now, in alchemy days, think about the 1700s in Europe. They had villages. One was called Paris, one was called London. You know, they were villages. They weren't giant cities. So to communicate from one village to the other was via two ways, walking or donkey. So things were slow. And the other problem is they didn't have a clear-cut way to communicate. For example, water. In this country, it's called water. In Mexico, what is it called? Not called water. Agua. What about in, I know I have some Russian speaking. What's, Voda. You know, my point here is, it isn't dihydrogen oxide. That's what every country understands water to be. So if I go to Russia and I go, I want some agua, they're going to go, So the alchemists had no clear understanding of how important a common science knowledge is. A beaker, it's a beaker. What's a flask? What's the concept of temperature? You know, all this stuff is not standardized. So it was very hard to duplicate another lab's, quote unquote, work because nothing was common. And probably most importantly, knowledge is power. They also didn't want to share their knowledge. So, especially in their kingdom, the king liked the alchemists because they used to do stuff that other people couldn't do. So anyway, those are some of the problems with alchemy at the time. Now, at the time of this confusing European science, we had other parts of the world doing science in a real solid way. Chinese, very solid science when Europe was in the Dark Ages. Middle East, same thing. And we don't recognize this. We think the source of knowledge, scientific knowledge comes from Europe, most people. They don't recognize that, guess what? The world was kind of big. And there were other very smart people doing things also in science. And much better, I might add. They were much more consistent than the Europeans. They were not as power hungry. I'm not saying they're not power hungry, but they were, had different reasons. Things like gunpowder came to Europe. Europeans did not invent gunpowder. Along with that are noodles. The Italians didn't invent noodles either. Came from China. This guy, I cannot pronounce his name. Does anyone speak Arabic in your Arabic? Huh? Can you pronounce this in red? Huh? And it's one is the son of, right? One of the words is son of. Anyway, this guy considered to be the grandfather of modern chemistry. Well, that says a lot. One, they're using the word chemistry. Okay, so the first European sorry. The first European, there's an error here. It's not hearing anything. I'm going to stop for a second and check whether okay. First European that proposed an atomic theory, his name was Dalton. Now, Dalton really was different than an alchemist because he believed that all the problems they were seeing with the alchemists was a very valid reason to not do that stuff. He also proposed bringing back Democritus' idea of the atom, the atomos, where before then it was Aristotle. Aristotle this, Aristotle that. Now, just because he said this doesn't mean everyone believed it. Just like today, there's a lot of controversy about science. Things like the status of fossils. Are fossils old or are they recently made? Controversy about that. Okay. So now Dalton believed there is an atom. He didn't know anything more about it than what Democritus said. No cut. He believed in the following. Matter is composed of indivisible particles. Now, when I say indivisible, it means that the atom is no longer an apple. That's the point of indivisible. atoms of a particular element are identical. So if you have a chunk of gold, all the atoms of gold are the same. Like, duh. Different atoms have different atoms. Different elements have different atoms. Another duh. Atoms combine in certain whole number ratios. Let's look at water. H2O. It's not H 2.1. It's H2. And then the fifth thing is atoms are merely rearranged to form new compounds. They're not created, destroyed, or changed, and that's not true. Atoms change all the time. That's called nuclear chemistry. But everything else is pretty solid. Okay, so along came a guy named Thomson, and he discovered the atom. Excuse me, he discovered the electron. And he also developed a new model for the atom called the plum pudding model. So, a couple things in this. One, there's a charged particle inside the model, and it was negatively charged. The problem was the atom was neutral. So he said there's got to be something that neutralized that negative charge. So he sort of discovered the proton. But he just formulated there must be something there to neutralize its negative charge. And he called it electron. Also, there's no organization of the electrons. They're just kind of roaming around there randomly. Okay. He also came up with the idea that these negative charges were a subatomic particle. Something was smaller than the whole atom itself. Now, it turns out the negative, or the electrons are significantly smaller. Like we're talking about 1/40,000th the size of an atom. Also, the atom was divisible. Divisible, I mean we can split it. He called the negative electrons corpuscles. I don't know why you got the word corpuscles, but anyway, we changed the name to electrons later, and I'm not sure when. And then they mentioned here the charged particles. Millikan. Now, excuse me, he knew that there were charged particles inside the atom, and secondly, they were negative. He determined the actual charge of the negativity. That's called charge. It's measured in coulombs. He did a very famous experiment called the oil drop experiment that determined that. Now, this was a guy that was very, very controversial. He wanted to prove Thomson's idea on the plum pudding model. So, remember, this is a retesting of theories. Okay, so his idea was we were going to take what is the short? He was going to take a big fat gold molecule and shoot it with a bullet. Now, he was expecting that the bullet happened to be an alpha particle, That's what this talks about here. But the bullet's a bullet. He expected that bullet to bounce back because Thomson's model said it was solid, just like a billiard ball, solid. So if you were to shoot a billiard ball with a BB, that BB is going to bounce off. It's not going to go through it. However, Rutherford's experiment found that everything went through. Very little bounced back. Something like 0.1% bounced back. Everything else went through, unimpeded. So this is really a giant departure from Thomson. Thomson said it's solid. Rutherford said, I got proof, evidence that it's not solid. Now think about that. This is 150-ish years ago, 180 years ago. I'm walking on, sorry, Rutherford, I'm walking on nothing. Two particles right through that. Can you pick up the gold? Sure. It's nothing. So this is the enigma that people at the time were going, you got to be kidding. You have got to be kidding. Now, he got the Nobel Prize for this, by the way. So what he came up with was the concept of nucleus. And the nucleus is a very abstract concept. He's saying that all of the mass of that atom is concentrated in an extremely tiny, tiny, tiny area. Because the only time that bullet bounced was when it hit the nucleus. Now, cool thing about that is, what about the electrons? Well, what about them? It didn't come into play in this experiment. So let me give you an idea of the perspective we're talking about here. Let's take an atom the size of a baseball, a professional baseball stadium, and take a marble and put it on the pitcher's mound. That's what we're talking about. That's how small the nucleus is compared to the whole thing. Extremely tiny. And secondly, what's inside the nucleus? Protons. And what charge are the protons? Positive. And what do like charges do? They repel. So within that tiny, tiny, tiny nucleus are these positively charged subatomic particles that want to repel each other, but are not repelling each other. So there's an extremely strong force involved in keeping them together. Extremely strong force. And see, these were all the enigmas that the scientists at the time were trying to figure out. Well, what's going on here? Why aren't they, that nucleus just flying apart? Lots of questions came up with Rutherford's experiment. Okay, so this is basically what's going on. Everything's going through except anything that encounters the nucleus. Okay, now that, by the way, that's a big deal, that Rutherford experiment. Big, big deal. It challenged every theory at the time because the data of Rutherford's lab did not match the current theories. So science had to change. Okay, Chadwick, so I'm doing some stuff on his own, and he figured out the mass of the atom didn't add up when you started adding up the mass of the protons. Now, electrons, mass mass was considered insignificant and they was counted as zero. It's not zero, it's just really tiny. But they counted it as zero. So he looked at the mass of the atom and the charge of the atom. And he came up with something shy. He said there's got to be more mass in the nucleus that's not charged to get this extra mass here. And he called them, because they weren't charged, they were called neutrons. So Chadwick is charged with neutrons. Now, down here it says, that was what he was proposing. That's not true. The masses are not equal. They're almost equal, but they're not. The difference between an electron, excuse me, the difference between a proton and a neutron is the mass of an electron. So if you add the mass of the electron plus the mass of a proton, you get the mass of a neutron. So what does that tell you about a neutron? This is a very interesting fact. Inside the neutron are two subatomic particles. Inside the neutron are two smaller particles. One is a proton and the other is an electron. So all the neutrons contain both a proton and a neutron. So everyone thinks electrons are buzzing around the nucleus, right? All but some are, but not all of them. Some are inside the nucleus, buried inside a neutron. Now, what's wild in nuclear chemistry, if we eject an electron out of that nucleus, what are we left with? That's called beta emission, ejecting an electron. What are we left with? Well, we start with a neutron, proton, electron. We take that electron out of the situation, what's left? A proton. So that atom now has one extra proton. So that atom is no longer the same element because it has more protons. Remember, protons determine what element it is. So nuclear chemistry, we transmutate elements all the time because we throw out neutrons, we throw out electrons, all this stuff. So elements are always changing. What the alchemists wanted to do, always changing. Okay, Ashton looked at a couple things. He looked at chemistry of atoms like carbon-12 and carbon-14. Chemistry of carbon-12 and carbon-14 is the same, but their mass is not. If their chemistry is the same, that means the electrons and protons are the same, but something's different between the two. And what's different is neutrons. Carbon-14 has two extra neutrons. So what Ashton came up with is the concept of isotopes. Okay, so we had this guy named Bohr, another Nobel Prize winner. Bohr said, there's got to be something to this electron bit. Nature's not random, like everyone's proposing the electrons are random. They're not random. And at the same time, he thought about the solar system. The solar system is not random. We have a sun, and we have planets that orbit the sun. And those paths are called orbitals. So he said, well, let's think of the atom like a small solar system. This is kind of like Orion's belt. Who knows what I'm talking about when I say Orion's belt?
Constellation?
What movie am I talking about?
Men in Black.
Men in Black. Remember the cat? Cat was wearing a collar. On the collar was the universe. Okay, so anyway, he said they're orbitals. And on the orbitals, the electrons are required to remain on the orbitals, no exceptions. They can move from orbit to orbital, but they can't be in between. So there's like space in between the orbitals that are off limits to electrons. And he said there are, because the orbitals are smaller, the closer to the nucleus, can only fit a certain amount of electrons on the smaller orbitals. The bigger orbitals can handle more electrons. And those are defined as 2, 8, 8, 18, etc. And tomorrow we're going to talk a lot about that numbering system. Now, the wild thing is fluorescent lights and Bohr, they're related. Now, can you touch a fluorescent light that's lit? Remember the old-fashioned lights, the incandescent ones? You touch them, they're hotter than heck. Fluorescent lights are not hotter than heck. They're not quite cool. LEDs are cool. Fluorescent lights are kind of warm, but LEDs are totally cool, yet they're producing light. Incandescent light bulbs produce light, but at the expense of a tremendous amount of heat and wasted energy. Okay, so Bohr explained that. He said, if we take an electron, nice and stable, and we zap it with some energy, we're going to zap it to a new orbital. It's going to jump orbitals, not go into the space that's not allowed. We're going to jump to the next orbital that's allowed. And it's going to require X amount of energy. Now, the problem with that new orbital, it's not stable up there. So what do unstable things want to do? Become stable again. So when that electron that's been shot up there with all that energy comes back down, it gives off the amount of energy that it took to get there. That's what you're seeing with an LED or fluorescent light, is that energy is in the visible spectrum, so we see it. Bohr came up with that. Nobel Prize material. Big deal. So we have an electron here at orbit number 2, and we nail it with some energy. I'm going to call that energy prime, a certain amount of energy. And that goes from ground state, which is the most stable part, of the electron, up to an excited state, which is unstable. That means high potential energy. High potential energy wants to become low potential energy. So what happens, that electron comes back down to the original orbit. Sometimes it comes down in steps, sometimes it comes directly. The bottom line is the original energy that took it up to that upper orbital is equal to the amount of energy either once or in steps that put it there. Those are exactly equal. And then energy is given off. Now, energy is in many, many forms because energy is in terms of wavelength. So we have infrared, we have visible, we have ultraviolet, we have X-rays, we have gamma, we have radio waves. All those are slow, going faster and faster and faster. So within all that mess are visible spectrums that our eyes, our cones and rods in our eyes are tuned to, are sensitive to. So the cones detect color. The rods detect black and white and how bright it is. So there's brightness and color. Now, if you're colorblind, your cones are messed up. Either all of them are messed up or some of them. So some people are colorblind to red. Other people are colorblind to green. Some people are colorblind for everything. You just see black and white. Okay, so that's a big deal with Bohr. Okay, so Bohr's got orbitals, number of electrons per orbital, and the fact that you can change orbits. Okay, this is where we are now. Now, this is old stuff. This is back in the 1920s. We're talking about this. Now, what the quantum model says, Bohr's model had some issues. The quantum model tried to think about the data available at the time and make better sense out of it in the new model. And the quantum mechanical model says there's no planetary model. You're not having electrons go around in orbits. That's the first thing. And the reason for that is Bohr, to have an electron go around in a circle requires energy. If there's no energy being given, it'll fall into the nucleus. And see, this model doesn't have that issue. Now, this model requires a statistical model perspective. And what I mean by that is, let's take a store like Rayleigh's. Now, this is going to be a very simple metaphor. Okay, Rayleigh's. On the side of Rayleigh's, there's a door. And by the door are a bunch of cigarette butts. And every now and then you'll see a smoker out there. And you know how smokers are, they flick their butts. My daughter smokes and I'm always on her case about flicking her butts. But anyway, so if we want to find cigarette butts, where do we go? We go to the door on the side of Rayleigh's, right? Do we know whose butts those are? No, it could be a customer or it could be an employee. We really don't know. We also don't know how they got there. That's the quantum mechanical model. However, statistically, if we were to go out there, will we find a cigarette butt? Probably not. But for sure, if we went to Rayleigh's, the side door, we find cigarette butts. So statistically, we know how to find them. That's quantum mechanics. Now, quantum mechanics came up with four ways to describe an electron. And that's the electronic configuration. Now, first level, the highest level, is called a shell. The next level is a subshell. The number of orbitals in a subshell, and the spin of an electron. Now, electrons have spin. the little top. And because of that, they have magnetic properties. So it's either a plus or a minus. So every single electron in an atom can be described by these four numbers. Shell, subshell, orbitals in the subshell, and spin of that electron. Now that's called electronic configuration. So if we look at hydrogen, hydrogen is very simple. It's one electron. We look at uranium, 92 electrons. So the configuration for uranium is much more complex. Tomorrow I'm going to show you that configuration. It takes a lot of screens to go through that, as opposed to hydrogen. Now the math to get to this is a real pain. In my quantum mechanics class, we went through all this stuff with Bohr and blah, blah, blah. We totally derived the mathematics for hydrogen in class. And it took about 2 weeks of math. And hydrogen is the only one we've done math on. Everything else is an approximation. So tomorrow we're going to spend some time configuring some atoms, both neutral atoms and ions. They're not the same. And this is what determines whether an ion forms or not, this electronic configuration. That's one of the reasons why I think it's important to understand electronic configuration. So when you get in your 2A or 1A class, this will not blow you away. But it's there to determine the most stable state of the atom in terms of its electron organization. There are certain organizations, electron organizations, that are more stable than others. And that's why ions form. Okay, so that's what I wanted to talk about today. This is where we are, quantum mechanics. Also, they renamed it from orbits to orbitals. And they make a big deal about the difference. One's physical orbit, the other is a statistical number to determine if you'll find an electron. And they're different shapes too. They're not all circular. In fact, Bohr's model is two-dimensional. Quantum mechanics is three-dimensional. It's another issue with Bohr's model. Okay. Notice no math.